Alright, one last video we talk about venturi effect. It's the effect that let's say when you let the fluid flow through a tube that we call somehow venturi tube, it's called change in pressure up on different between the cross-sectional area of the tube. Actually, this venturi tube is a device that used to measure the flow rate of a fluid that can be either a gas or liquid. So you let the fluid flow in and you apply the Bernoulli equation to find the relationship inside the Bernoulli equation. If you want to look into details of this venturi effect, you can go to the link that given here. I would just want to speak in short about this venturi effect, and this is let's say the last part of the fluid mechanics and also fluid dynamic. So if you go to some exercise, we have a venturi effect. Oh, I forgot to mention about this. You can measure the pressure difference between two positions. Let's say in this case, position 1 is here, position 2 is here, by looking at the difference between the fluid height. That is here. You know the difference in pressure, and you can relate all of this to the parameters you want to know from the venturi effect. Okay, let's go to the exercise. So assume that there is a fluid that flow in the venturi tube. You know the speed of the fluid at position A. Here. Actually, you can say that this is the speed of fluid at this cross-sectional area, because these fluids obey the flow of this fluid obey the equation of continuity that we have learned before, right? This can be A1, this can be A2, let's say. But okay, now we know the speed at in this section. In the first section that equal to 9 meter per second, and the second section that equal to 10 meter per second. The question asks you what is the difference in the level of the fluid in the tube at position A and B. I should write this A and AB, something like this. But anyway, we try, because now we don't know the cross-sectional area of the region A and region B, of the tube in the region A and region B. So in this case, we can try to apply this Bernoulli equation. So to recall the equation again, write down everything. Let's say PA plus low GHA equal to, not complete, plus half low VA square equal to PB plus low GHP plus half low VB square. And alright, to know the difference between the level of fluid at position A and B, we need to find the difference in the pressure PA and PB, right? And in this case, this low GH can be cancelled out because the position of I can write down here. This is point A. Shouldn't use this. Let's say should use this instead, 1, 2, right? Not so really. No, it doesn't matter. A and A, B. The pressure that the pressure difference that caused the difference in the liquid in the liquid level in these two small tube is the pressure at PA and PB here. So we can just that because VA is larger than VB. Sorry, VA is smaller than VB, right? So PA should be larger than PB, and you can write this. Oh, sorry. You can write it. Reduce this Bernoulli equation into this shorter one. Then you can find that half. You don't know low, right? You don't know low. Yes, that seems to be a problem to do a direct calculation here. But this is a trick. This part can be actually treated as not really, but you see that it's like probably I'm not good in drawing, but try. You can treat this part like a flow of this is A and this is B, something like this, and this is the fluid. The pressure that places the fluid up in the small tube A is PA, and the pressure that places the fluid up in tube B is a PB. So in this case, you know that PA minus PB should equal to the difference between the height of fluid. It's nothing else. Then you combine equation 1 and equation 2, and you get you can cancel out the density of the fluid, because here you don't yes, you can. You don't need to know the density of the fluid at all, right? You want to find delta H, so you can say delta H equal to half VB squared plus VA squared, and divided this all by G. Okay, already put G here, right? No, because I still didn't put the value of V and VB, so let's make it. And in the end, this is equal to VB squared, that is 100. VA squared, that is 81. And you can already multiply this 2 by 10, and then you get about 0.95 meter. It will be 19 divided by 20. Alright, and this is the answer. Another example of venturi effect. I hope I have enough space to show you the solution. No, not only the solution, it's how to find the solution. Let's do this. We have in this case we let air flow through the venturi tube. And at the bottom of the tube, at position X and at the bottom of the tube, there is a U tube that connect between two positions 1 and 2. And in this U tube, there is mercury. Yes. Okay, let's say that because of the difference in the pressure P1 and P2, this should right this way P2. This is A2. Right? This is A. This is so many things wrong. A1 and A2, right? It's not so. This is bad picture, right? A2. All right. Okay, everything should be fine. Now, find V1. Seem to be easy, but probably not, because we still don't know V2, right? We know A1 and A2. You can guess that in the end, you need to find V2 to get V1 from this equation of continuity, right? This would be the key equation. Okay, let's think about that. But, well, no. Well, if you don't know what to do, three things that you would take into account to solve this problem is the equation of continuity, right? Or continuity. Second is you need to think about the things to find the relationship between two sides of the U tube, because you know D. And this is P1, this is P2, so you can write down this is 11 centimeter. Alright, so it's 0.11 meter. Then you can say that you know that P1 should be larger than P2, right? That's why the height here is higher. Let's say let's say P1 minus P2 equal to low Hg G D. But you still don't know P1 and P2 anyway, but you know the other P now. And this is about 14960 Pascal. Okay, I should mark this answer 2. Third, we will apply the Bernoulli equation. You can say that P1 plus, because low GH would be the same, right? And position here, that you measure P1 here, and position that you measure P2 here on the same level. On the horizontal line, so you can just cancel out low GH on both sides of the equation, and then you get only this V1 squared equal to P2 plus half low. This is low air, right? This is not. This should be the density of the air. It's not the density of the mercury. This should be something like this, and again, you can find delta P that equal to to v1 alright, v2 square minus v1 square. You know that the air density is 1.2 kilogram per cubic meter, so you can really put this you get I should put this 2 here, so I should use this to name the equations that we're gonna use to combine to find the final result. And alright, now we know delta p. If we put the delta p from equation 2 into equation 3, we will get this v2 square minus v1 square equal to 14960 divided by 0.6, right? We know this. And we know a1 and a2. We can already put the value of a1 and a2 into the equation 1. Then we get like we want to find v1, right? So we get v2 equal to v1 a1 divided by a2, a1 divided by a2, and simplify it. Am I right? a1 divided by a2, alright. Then this gives us v2 equal to 4v1. This seems to be easier, right? Yes, we use this equation. I will call it equation 4. Better call it equation 4. And this is equation 5. We okay, I will write here 2 plus 3 get equation 5. And 4 and 5 we get 4 and 5. In the end we get 2 equations, 2 variables, so we can solve for v1. Yes, we should solve for v1, right? Yes. So we put the value of we put equation 4 into equation 5, and we get 4v1 square. No, this would be 16v1 square minus v1 square, right? Equal to 14960 divided by 0.6. Then we can say v1 equal to this 15960 divided by 0.6, and this will be 16. We divide this by 16 and put the square root here, and the answer will be about 40.77 meter per second. Okay, that would be it.